So in other words, if I have a similar problem, want you to solve it. So then, if you have the metric elements like this, so for instance, if I want to calculate expectation value of psi NLM, and this x, LMM, like this. So what you do, you change this x to r, the sine theta cosine phi. Then the wave function also change in terms of the radial part, which is the radial part r and l, and then r part r and l, multiplied by the y lm, and then have r sine theta cosine phi, and then here's y lm, like this. So that's what I meant. In other words, we're going to separate these two terms this way. So then you will be able to calculate. Now, if I have n prime, l prime, prime, and you can do the same thing, prime here, prime like that. So that will be expression in this case. Now this integral, I have to give you the equation if I want you to do the calculation. So that's the difference. You need to be careful in the sense that if we're looking for the expectation values like this, and you do the calculation. If we have LZ, we will be lucky. But if we have LX or LY, you make sure in the exams, we need to change this guy, these two ones, L plus and L minus, like this. You do not want to directly use the operator apply this. You're going to convert this one, then you can use the identity, which is the equation. If you apply on this, and this is going to square root. This pen's a little bit thinner. Let me see whether I can read this. Oh, not too bad, but it's slightly worse. Okay. L plus 1 minus m plus 1. And then here's a y, ln plus, like this. So that you need to be careful in this case. So this will be y, ln plus. So essentially, if you are given to you lx or ly, you're going to convert to l plus l minus. Can I give a thumb up, everybody? Give a thumb up. In other words, if you got lx, ly, and then what you need to do is you make sure all of this has to be in this particular format. Okay. If you're lucky to get LZ, then there's no need of calculation because LZ just eigen value essentially like this yi. So you're lucky. But if it's LX, LY, then you can do something like this. Okay, that's all that I have. Let me just look at this. Okay, very good, very good, very good. And let me keep on going this because it's somehow is a good place. I want to have a better pen. This pen is a little thin. So in other words, just make sure you remember that. I'm going to use another board to show you. It's a little bit of a summary about what we did for the hydrogen atom. And I think it's a good idea to summarize it in such a way that you guys have been able to see the entire picture. The slide that I showed you, you already gave you some ideas to do the calculations, but it's not a complete idea for the moment. So I want to summarize it. And so this is the absolute minimum hydrogen atom summary. Hydrogen atom summary. Hydrogen atom summary. So the summary, it turns out I thought this is quite important what you definitely absolute minimum. You need to remember this. Otherwise, people will say, "Did you learn hydrogen atom at all?" So this is the absolute minimum. First eigen energies. So eigenenergy En 13.6 electron volts divided by N squared. So this is the absolute minimum. You need to remember the eigen energies. This N is a main quantum number. Start from 1, 2, all the way up. And this is called the main quantum number. So N is the main quantum number itself. So this is called the eigenenergy. And now we also have eigenstate. We use a wave function to represent that. This wave function is a psi. I already showed the slides. R, theta, phi, like this. In principle, you have three variables, R, theta, phi. And then here you have the radial part, R and L. And then angular part, theta, phi. Now, if you want to add the lowercase r, that will be good, which is the radial part of the wave function. This I already showed the table, and you already see that in the table. And I want to explain each one of this. This L here is called orbital angular momentum quantum number. It starts from 0, 1, all the way to n minus 1, like this, all the way to the n minus 1. And this one is a very strange notation, as I mentioned last time. This is the way enforced by, in some sense, chemists. Because if we do not have chemistry, we probably start with 1, 2, 3, like this. Because chemists, they use this one, so we are enforced. So you see how strange things from 0 to n minus 1. In fact, what happens, this guy actually dominates. And L is the one in control. L is the one in control. If L equals 0, everything will be s orbitals. L equals 1, everything will be p orbitals. But now since we swap this, so in other words, we make this n become the main quantum number, and then everybody else has to adjust. In other words, just like, suppose if your L is controlled, then everything will be adjusted. But now, this is not the way we did. You see, this guy is called the main quantum number. If this is the main, this is orbital. So therefore, you see, it starts from 0 all the way to n minus 1. And for n equals 1, which is s orbital, all the way 1 s orbital, and this only L equals 0. So I'm going to show you a table here. For instance, n equals 0, n equals 1, L just equals 0. So you have no other ways to do that. And then, if n equals 2, then my L can be 0 and 1 like this. So you have 0, 1 like these two. If n equals 3, then L is 0, 1, 2 like these. So they are enforced by this one. But now, all the L equals 0, these are the s orbitals, s orbitals, s orbitals. And all these are all s orbitals. Even you have 4, will be L equals 0, 1, 2, 3. This is our s orbitals. And this is the one that I mentioned many times. Numerically, if you solve for this, numerically, if you solve the equations, for instance, if L equals 0, you will end up with the result n equals 1, n equals 2, n equals 3, n equals 4. In other words, in principle, this L is in charge. When L equals 0, whatever you get, these are all the S states. So the entire diagonalization will give you all S states. But if L equals 1, all the diagonalization will give you P states. Does that make sense to you? So that's the key. So in other words, that's why n can be infinitely large, but L will be controlled by this n. So that's the kind of strange behavior. But normally this n can be infinite. So that's the point that I want you to remember it. So these are S states. Now, when L equals 1, this will be P state, P state, P state, like this. We will call it 4P state, and 3P state, 2P states. But there is no 1P state, so that's not utilized. So this is the geometry of what I want to. Now, one more thing before we close this is another one. When we write on the wave function here, when we run a wave function, for instance, if we run a 1s state, just give you an example, and if I want a 1s state, so then the wave function here will be R10. So this is the 1s for the R10. That's s state. Now for the 2s state, you will write a R20. That's 2s state. 3s state, R30. This f state, this df, this is sort of the s state, 4 zeros, like these ones. That's called the radial part. And then if for the p state, and you're going to write an R21, R31, R41, like these ones. And these are the NL states which you have. Radial part. Now, angular part, it has Lm in it. This M, called the magnetic, start from negative L all the way to positive L, like this. That's a magnetic projection up to this. So in this case, and you will see another column comes over here. So this is another one which is going to be utilized. I hope I do not use too much time away, but this is quite important in this case. Suppose I want to say I want to utilize another column. This allows me to show which state is going to be relevant for my y and m. So now y and m comes out. So because L equals 0, the m it will choose one value. So this would be y 0, 0, like this. So that's the angular part. And the angular part for this one here. And now this is for the S state, still the L equals 0. This L equals 0. This is also 0. But now this L equals 1 now. L equals 1. Now this m can take 3 values. You can have negative 1, y 1, 0, y like this. So in other words, this line could be like this line like this line like that. So for the p states, it starts to split into 3. And that's true to this state. Now if you have S state, and here you also have the 0, 0. So the angular part, they will be always exactly the same. So you see the angular part, there's no difference here. Exactly the same, y, l, like this. But once you start to move on to L, and that will be, this is going to repeating whatever we had before. And for the 2, this will be the same thing. So there is no difference. And sometimes a little bit confusing, but it was this M caused a lot of problems, because when it went L, you will have a situation like this. And you may wonder, what is the bottom line? Well, bottom line that I want you to remember is this guy's here. y0, 0, 1 over square root of 4 pi. And this, you need to remember that. And that's normalization self. And now 1s orbital. 1s orbital, the wave function, the spatial distribution look like this. So if you plot R10, this is the spatial distribution of the orbital, not the orbital density, just the orbital itself. And this has a peak like this. And this peak is R equals A0. This is the Bohr radius. So the maximum is the Bohr radius. This is the absolute bottom line. So now you see this is self-consistent with Bohr's model. So Bohr's model, the maximum at this point, but he's a classical model, so there's a new distribution involved. It's just one single orbital. So this is the one which I want to show you. So, and the actual density, the probability density, rho density, just equals R squared R10 like this. Just remember, this is R times R, capital letter R, not R squared sum. In other words, it has to be these modeled by each other. So that's the big difference. Regular wave function, you do not have this, but this has to be squared in this way. Okay, let me see anything else. I think that's it. That's pretty much that I covered everything. Looks good. All right, so folks, let's go back to the Zoom. So we are going to move on to a few questions. First question, does the non-degenerate perturbation field cover all the eigenstates? Tobin. Does it cover all the eigenstates? Perturbation? No, yeah, of course. This is not, because we only specify one particular state. All right, that's good. All right, next one. Okay, Cody, what is the first order energy correction? Eigenenergy correction, E1. First order energy corrections. First order energy corrections. What is that? Anyone else can help? Okay, what is first order energy corrections? So first order energy corrections. Aisha, do you remember that? First, look at the notes, look at the notes, look at the notes. What's the first order energy corrections? So the first order energy corrections. Yeah, what's that?
Is it diagonal? No.
Yeah, keep on going, keep on going. Because what? Yeah. Anybody else? Alex, can you help? What is E? First order energy correction. It's in the book, right? We read the book yesterday, last time read the book. First order energy correction. Let's look at the book. Let's read the book. So this is the equation 5.1.10. Did you see that? 5.1.10. Did you see that? Did you see that? Yeah, look at the page 135. Did you see it? So this is the first order energy correction. Make sense? Could you guys write this down? This is so important. This is absolute minimum. You know, this is the energy, first order energy correction, which you need to remember. Okay, I think I typed this here. Yeah, you see here. Yeah, that's very good. So that's the first order energy corrections. So this is the one we have. So you see that. And now the wave function. I don't want you to write this down now. Oh, I do want you to write this. Forget me. For the wave function correction, and how do you remember this expression like this? The wave function corrections like this. Here's what I always do. In the sense, we know there's a summation, m naught equals k. And this part is really, really very good to remember. How do you know that? So the eigenvalue, the eigenenergy correction is just the expectation value of your perturbed, the Hamiltonian H sub I. But this one here will look like the first part. Do you see you have these brackets? So you're going to write on brackets here like this. Here brackets like this way. Okay. So that's that. And now let me move these brackets over here. So this is the state k. So here you're going to write a phi k here. Here brackets is a phi k. It's the exact same. And then all you need to do is make another bracket which is phi sub m h I. So this is the perturbation Hamiltonian. When you insert this one here, you have another one in the following. And the denominator will be epsilon k minus epsilon m, like this. So the way that I remember this, I think I wrote down in my slides. Yeah, how to remember this? The way that I remember this once I have this, I will have this angle brackets. And then, remember, whenever the energy is closer, that perturbation will be larger. So therefore, you must have a denominator. Because when you're closer, the energy contribution must be larger, or the wave function contribution must be larger. So these must minus each other. If this is the angle brackets is a Kate, and this must be bra. So bra Kate, in other words, so these two must be bra. Here must be bra, and here must be Kate. So bracket, together in this way. So that is what you will get expression like this. So this is how I usually remember that. Let me see anything else. I think that's it. So usually contribution is larger, so the closer. Yes. So this is what we learned last time. And I think I didn't need a zoom, folks. We can stop the zoom now. So we don't need this now. We exit this. Okay. Bye-bye zoom. And now we're going to keep on going. And I spend sometimes, and I hope this is a way for you guys to remember that. All right, so this is the so-called non-perturbative, wave function. And we read through one example. There is another example. We will not going to read them because it's slightly complicated, but I just want you to appreciate the result. Could you guys turn to page 142? Equation 5.2.24. So that's equation 5.2.24. This is the equation which we all need. On page 142, page 142. So that's the page which we have. And this one is extremely interesting. So the energy correction for the van der Waals force, in this case, the energy correction should be energy correction, not force. Energy correction is proportional to C over R, sixth order, like this. Could you guys write this down? And van der Waals force, you remember, van der Waals force is the energy one, which is purely quantum mechanical. And if you even have a neutral molecules, you still have this particular feature here. Here what we said is essentially two hydrogen atoms like this. So H1, H2, like this. Now the reason I emphasize this, you probably did not appreciate why we doing these things at all. This was really non-trivial. Because if you do the classical way of calculating, you won't end up with this particular results, which I'm going to explain now. In other words, in this case. So this is a one which is quite important. So let's look at two hydrogen atom. So I'm going to write this down over here. So one hydrogen atom, we have one proton here, another proton here, and here is one electron, negative charge, one electron, negative charge, like this. Okay. This problem, you think it is simple, not simple at all. Now, suppose I want to arrange these four charges on the same plane. Four charges on the same plane, to ensure there is no net force on the entire system. You understand what I'm saying? In the session, all these four charges on the table, you can make sure that when all of the charges has no net force. Let's try three charges instead of one. Let's say I'm going to put this negative charge E here in the middle. No problem. So you see there's no net force on negative E2, right? Negative E. So there's no net force because of this attraction here and this attraction there. Then there's a problem. This charge will experience a net force pulling this way. Did you see it? And also you get a net force pulling that way. So therefore there's no way you can balance this. Does that make sense to you? So in other words, there's no way you cannot have a static way to do that. The only way you can do, you have to orbiting around this whole thing. That's why the classical theory best can explain this since you use orbiting. There's no other way to do that because you cannot balance this. Statically cannot be zero force. That's why quantum mechanics becomes so important in this case to describe all these features. What is even more strange is the following. If I have two substances completely neutral, there's no charge whatsoever, completely neutral, net charge is neutral. But this charge oscillation still occurs. So this is neutral, and this oscillation is due to this factor comes out, negative R6. So this is only can explainable with the quantum theory. You can't explain with the classical theory because it's not possible, because this is neutral. Q equals 0, Q equals 0. Cody, when the Q equals 0, so what happens? There's no attraction whatsoever, right? This is neutral. But now when you try to fluctuate, this fluctuates, the quantum fluctuates, and they have attractions. So even neutral molecules can attract with each other. That's due to this quantum effect. Okay, so this is so far, we just mentioned the so-called non-degenerate perturbation theory. Now, today's job, our main focus is on the degenerate perturbation theory. And this one slightly more exciting, instead of not overly complicated than the non-degenerate perturbation theory. And so we're going to talk about this now. So this is my section number 2, degenerate perturbation theory. So just use simply as a PT. So this is degenerate perturbation theory. The perturbation theory now is degenerate. And this degenerate could be also nearly, suppose could be added nearly degenerate. It's not 100%, but yes, it's very close. So the first thing that we want to explain, why we need this rationale for degenerate perturbation theory. Why we need a degenerate perturbation theory? I just simply use a D to representing that. The main reason is the wave function. You see, the first order wave function have this particular shape. So have this particular shape. So the first, the wave function have this particular shape. Now, normally, if k not equals m, you are fine. You have no problem. But when they start to degenerate, there is a problem. In other words, even if m not equals k, if k is not equal, but epsilon k, epsilon m, they're equal to each other. You know, the indexes are not the same. But the eigenvalues will be the same. And this happened to the p orbitals. Let's look at p orbital. You see you have p orbital. We have a px, py, pz. These are all degenerate. Has exact same energy. Whatever the energy is exactly the same. Now, when you have a external perturbation, you run into the problem. Do you want some of this particular energy level or not? So that's what happens. If this happens, then it diverges. When this happens, it diverges. The wave function diverges doesn't make any sense. You cannot have a wave function diverges. So that's not possible. So therefore, this is our rationale to describe the degenerate perturbation theory. Now we're going to use a notation to be more precise. So our notation is as follows. The unperturbed wave function we will write an epsilon k. This k will have the index when a equals epsilon k2, a equals epsilon k3, a equals epsilon k mu, like this. In other words, what I'm saying here is that we have a bunch of these states, they have exact same energy, all close by exact same energy. And that's a notation. This 1, 2, 3, this eta referring to degeneracy. So order degeneracy. If you say double degenerated, then which means this eta equals, this mu equals 2. For our 3p states, this eta, this mu is going to equal 3. So this way the mu equals 3. Like this. So this is the mu equals 3. So that's usually called degeneracy itself. So now I'm going to show you the key steps of what you need to know. All right, that's a key step. We will again read the book, and that we will understand better. But I want to show you the key steps of what we will do. So that way, when we read the book, we will be able to follow. And you probably remember, we always do the first. Do you guys still remember in the non-degenerate perturbative theory, what's the first step? Alex, what's the first step when we do the perturbation theory? First step. Any idea, Coben?
Not the Hamiltonian, but with the split.
Exactly. Did you guys hear it? Did you guys hear it? We will split the Hamiltonians. Always the case. Could you guys write this down? This things started repeating. So when we write books, we want to repeat the same message again and again. So this enforces you. So split H into 2. So split H equal to into 2. So essentially what we have, and you're going to get bored from me now, because we do the exact same thing again and again like this. Okay. So we do the exact same thing. Again, split the Hamiltonian into 2. So that's what we do. And all right, now this lambda you recognize, this is just a parameter, variable parameter, allows you to monitor the orders. That's what we do. Second step, we do the exact same thing as we did last time. The only thing that is slightly different is as follows. And I want you to keep in mind how do we do that. The second step, we will expand the wave function. So this is the original, assuming correct wave function you're going to have in terms of, now watch carefully, of phi k1, phi k2, phi k3, all the way to phi k mu. Okay. By the way, this is exactly the same thing we've done here. Did you see here? Did you see we expand the wave function? Did you see here? In terms of m. Did you see that? In terms of m. Exactly the same. But here we also expand the same way. There's no difference. So always expand. It's the way we expand things differently. So, but different from non-degenerate perturbation theory. NDPT, non-degenerate perturbation theory, but differently. Not exactly the same, we do it differently. So here's what its difference is all about. So here's what I want to show you. And this part, it is more involved with the metric elements, like this way. So we're going to expand this one now. So this expanded like this. This expanded. So the expansion is in terms of like this. Equals. Since we have a number of mu, so we will start with mu equals. Sorry, it should be I. Okay. I all the way to mu. In other words, when we expand this, I want you to pay close attention to what we are doing here. In a non-degenerate perturbative theory, this M runs for all the states. But here, when you run it, it only runs through these states. It won't run these 3 states. So in other words, so then the first is the coefficient second is phi k sub I. So I will highlight in blue. So this is a restricted to a small set. This is restricted to a small set. Here is to all the states. So here is to all the states. But there we restrict a small set of the states. So only small set of states will be in our view. In other words, we do not expand all of them, but it's a small set of states, which is we will be included. Not all of them, just small set of the states. So this is one thing we will work on. Now, did you see my C has no superscript? This C is going to equal C 1, 0. This means zeroth order. You see, we are expanding the coefficient. You see, we're expanding the coefficient itself. And this is zeroth order plus the first order. And so that is the two orders. And then we will have subsequent orders, lambda squared, ci, 2, and the remaining terms. This will be utilized. And I don't want you to be discouraged from this expression, in the sense that you will say, Dr. Zhang, wow, all these terms will be included. Well, most of the time, the maximum we stop over here, just 2 terms. So the rest of them just scary, but we never use it, essentially. That's what we did. And now the energy we extend in this following way. Ek 0, first 0 order, and then we do the same thing. First order, and lambda 2, second order, squared, and keep on going like this. And this is the only difference which you will see me to write. In other words, 2 restrictions involved. One restriction is the number of states is very smaller than what we had. Essentially, we were just working on those subspace, which we have that. And now, finally, we are done, basically. We're going to substitute everything. Then use equation here, 1. This equation inherited on the top. They are same equation. Essentially, it's a C and 2 like this. So these are the same equations. We will plug 1 and 2 into the original eigen equation, Ek plus Ik. So this is the equation. We're going to plug that into it and match the coefficients. Coefficients of lambda. Going to be lambda 0 or lambda 1, lambda to the power 2 like this. So that's the match coefficients. So this is what we do. So this essentially the entire calculation is like this. And then once we match the coefficients, and we get the results that we need. So again, split the Hamiltonian, expand these wave function in terms of these states, and we'll restrict to that. So that's a key difference. And expand the coefficients, and plug these 2 into that equation and match both sides. That's it. So there's no more things to learn. And before I let you guys read the book, and I want to show you the key message here. Because if you forget about this whole things, and then key message is very important. What you're going to see me to write them down is essentially we form a matrix. Form a matrix like this. Phi, K, I H hat phi k j. The key message is that we'll form this matrix and diagonalize it. So in other words, if you forget everything about degenerate perturbation theory, do not forget this box. Form the matrix, diagonalize it, and you get everything that you need. So that's the key message. Okay. Remember, we will quiz you on this in the future quizzes, and as well as that. We still have a few minutes. We're going to read the book, folks. We're going to read the book, and I want to show you. So this is on page, or section, I forgot the page number. Section 5.3.2. Let's go ahead and let me check which page. Yeah, this is the 143. Page 143. And this time we're going to read. Let's start with the Toby. Toby, could you read one page 43? Section 5.3.1. I only need to do the second paragraph. Degenerate perturbation theory expands like this. That's all you need to start.
Degenerate perturbation theory expands psi sub k in terms of a group of degenerate or degenerate eigenstates phi sub I. That's squared.
No, the second. The second is the bottom.
Phi sub I to the second order as psi sub k equals the summation as I equals 1 c sub I phi sub I, where c sub I equals c sub I to the 0th order plus lambda c sub I to the 1st order plus lambda squared c sub I to the 2nd order plus ongoing. Our job is to determine c sub I to the 0th order and c sub I to the 1st order. E sub k is expanded similarly as e sub k equals e sub k to the 0th order plus lambda e sub k to the 1st order plus lambda squared e sub k to the 2nd order plus ongoing. We substitute both psi sub k and e sub k into h hat psi sub k equals e sub k psi sub k to get the quantity h hat plus lambda h hat sub I closed quantity times the summation as I equals 1 of the quantity c sub I to the 0th order plus lambda c sub I to the 1st order plus lambda squared c sub I to the 2nd order plus etc. Closed quantity times phi sub I, which equals the quantity e sub k to the 0th order plus lambda e sub k to the 1st order plus lambda squared e sub k to the 2nd order plus etc. Closed quantity times the summation of c sub j to the 0th order plus lambda c sub j to the 1st order plus lambda squared c sub j to the 2nd order plus etc. Closed quantity times.
Okay, thank you. Yeah, thank you so much. Cody, could you continue? We purposely choose.
Well, we purposely choose I and j as indices for two summations for c sub I and c sub j because they are completely independent. Equation 5.3.2 is the mother of degenerate perturbation theory. The following step resembles non-degenerate perturbation theory. For the same lambda, we match terms on both sides of the equation.
Yeah, keep on going.
We have lambda to the 0th order. For lambda to the 0th order, we have the summation of h naught hat c sub I in the 0th order phi sub I equals e sub k at the 0th order summation of c sub j at the 0th order.
Hold on 1 second. Do we understand the equation from 5.3.3? From 5.3.2. Essentially what we did was we just checked our lambda zeros terms, match both sides. Okay. You can take a look at this. You see zeros terms, in other words, whatever the lambda exists, we should do not consider them. So the only thing that you will have is just h0 multiplied by c sub I to the 0th order. So that term that left. All the remaining has all these lambdas, we're all gone. And then on the right hand side to do the same thing, just e sub k and superscript the 0th order multiplied by cj 0th order and phi j. So that's the only term that remains. That makes sense to all of you? 5.3.2. And then Wednesday, we will keep on reading this until we finish the first and then first order perturbation theory. Essentially, degenerate perturbation theory is first order. When we're done with first order, that's start as ends here. So essentially, in some sense, it's simpler than non-degenerate perturbation theory. All right, good luck to you all. Once I grade the homework, and I will leave that in your mailbox, and I will let you know when I did. Not yet, I will do it quickly as possible and grade them. Now, when you prepare for the exams, if you are doing the weekend, just send me an email if you have questions. And make sure you do check your notes